Hello all, my name is Jacob Moss, and I'm here today with Ella Jones and Milo Johnson, and today we're going to be tackling our Physics 213 project number 1. Just to get started off, I'm going to be giving you all a brief description of the problem that we have chosen, and I'm going to be providing the basic concepts, assumptions, and physical representations necessary in order to get an understanding of what's to come. Let's start off with understanding the overall problem. We have been tasked with looking at a very thin strip of charge with several key properties. The first of which is that this strip is very wide in the x direction, not exactly defined yet, while maintaining a given length of 2L in the y direction. The next important bit for us is that the center of this strip is at the origin, which allows for some easier calculations and a set of simpler physical representations. We've also been given the charge density of the sheet with the value of sigma is equal to sigma naught times y, and that's all over L. Our ultimate goal with these pieces of information is to determine the electric field as well as the electric potential at every point along the y-axis, while y is greater than L and v is equal to 0 at 2L. The last of these two things is a little vague in nature, but I'm going to be explaining it in more depth shortly. Actually plays a pretty critical role in all this. All right, we're going to keep on going with understanding the problem here. Next, we're going to be looking at all of our quantities, and we're going to be figuring out what they mean. The most important piece of information we're given is the charge density of the sheet of ours. Thankfully, we've been given a relatively simple linear charge distribution of sigma naught times y over L, as mentioned before. In the following slides, there's going to be an isolated graph of this distribution for some better representation, but essentially what this distribution tells us is that as we move further along the y-axis in the positive direction, the overall charge is going to become increasingly positive, while the opposite is true for the negative side of the sheet, and that's represented by the diagram shown here on the right. The next quantity we're given is a voltage of 0 at the point along 2L, which was given in order to obtain a point of reference for the voltage given off. That is V as the voltage. The only other quantities that we're given are L and sigma, which are rather arbitrary distance and initial surface charge densities, respectively. These don't really play vital roles in everything until you get to the integration portion, but you can really just assign values for the sake of this. All right, next we're going to be going over some assumptions. The most important assumption that we made is that the sheet has to be infinitely long. That way we're able to apply a concept that we're all already familiar with and relate it to the charge of a single long wire. Our goal is going to be to apply integration methods in order to split up, like quote unquote, split up this sheet into an infinite number of these infinitely long wires, then calculate one of them so that we can add them up over the area that we have been given in order to find the total electric field and potential given off by these charges. Another important thing to look at is our axes, which are going to be labeled kind of unusually compared to conventional Cartesian coordinates, but this is just for our graphs to look a little more sensible. I think you'll appreciate that. All right, and then lastly for me, before moving on to Milo's calculations, I'm just going to be going over a few physical representations, and now these are pretty key to working through this problem, as well as creating a prediction of what we expect from the sheet. The first graph here on the left, I referenced a little earlier, and it shows how the charge goes from negative to positive as you move into the positive y direction. It's relatively straightforward and given to us directly from that equation. The next graph is in the center here is our expected voltage graph that we were able to create from what we know about the charge density of our sheet. Since we've already determined how the charge is laid out, we know that the voltage to the left side of the sheet is going to become increasingly negative as it nears that negatively charged side of the sheet. And this is going to result in an asymptotic function that goes through very small voltage as we approach negative L. Then after we cross over the sheet, the right side is positively charged. So we see a similar effect moving away from the sheet. The closer to the right side of L you are, the higher voltage you're going to experience. And it just dissipates the further you move away from the sheet along the y-axis. Also note in that graph there that the intercept at 2L, where the voltage crosses back over the axis, that's due to our given reference point as stated earlier. We're going to do more with that later. Then this third graph here on the right is our electric field vector map, and that just shows the strength of the electric field while near the sheet. As you can see, the positive charge repels while the negative charge attracts, and this causes a uniform direction of the electric field through all of space and an equal magnitude for all spots along x holding y constant. So that's pretty much all there is for me today. I'm going to turn it over to Milo, and he's going to go over some calculations for you guys. Thank you all for your time.
Hello folks, and welcome to the calculation section of the infinite strip in the xy plane with some charge density. So first thing we want to keep in mind is our equations and principles that we are going to use that will be very valuable when solving this problem. The first thing we want to keep in mind is that surface charge density can be broken down into a bunch of infinitely charged areas of infinitesimally small dimensions that can then be integrated over to find electric field, total charge, and things along those lines. This is opposed to linear density, which is charge associated with a very small length along, say, a one-dimensional wire. The general equation for the electric field of a point charge is given as kq source over r squared times r hat. This can then be broken down into infinitesimal electric field vectors that are accumulated from all of these point charges of a continuous object, for instance. Now, the equation that's going to bind this whole problem together is the equation for the electric field of an infinite wire, which is given as 2k lambda charge density of the wire divided by s times s hat, where s is the distance between a reference point and the wire, and the s hat is the vector pointing away from the wire. We want to keep in mind also the relationship between electric field and voltage potential, where if we think of voltage potential as a sort of surface, any point on that surface and the steepest rate of descent in that surface will give the electric field at that point in space. which is essentially what this equation is saying, where you're taking the electric field to find the negative gradient of that voltage surface. Now, you can do a reverse function of that, whereas a derivative is a large amount of derivatives baked in there. The inverse of a derivative to get back to the voltage potential is taking a negative integral. And that's exactly what we are going to use in our problem, where if we know the electric field across a surface, we can integrate it over some certain sections, these R initial to R final, to find our voltage potential difference for all points on a plane. So to start off with, we know that from our initial setup, we're going to have some positive charge on this side of the wire and some negative charge on this side of the wire, where the y-axis is pointing this way and the x-axis is pointing this way. Again, note that inverted axis, which I will carry on for the future of this setup for the problem. So let us first divide this strip into a bunch of very small wires with a thickness on the y-axis of dy. Now, why did I do that? Well, if we divide all of this strip into a bunch of infinite wires, we can use this equation to find the electric field influence on an arbitrary point A on the y-axis, which is some distance y greater than L. And we can find all of these accumulated electric fields on this point to find the net electric field that is generated by this entire strip. Now, how we go about doing that? First things first, we have to find our linear charge density of each of these wires. And we can do that knowing the charge density of our strip. If we wanted to find the linear charge density of each of these wires, all we have to do with this equation is multiply this linear charge density by that thickness, because this is in coulombs per meter squared, and if we wanted to find coulombs per meter, we multiply it by a certain thickness so we know the amount of linear charge in a specific thickness. So now that we have our infinitesimal linear charge density, we now must go about finding this S value. Well, the way we can start by doing that is thinking like we have to find the distance between A and this infinitesimal wire. This infinitesimal wire, we'll say, is some distance y from the x-axis. And we know that A is a distance A from the origin. So the distance between the wire at all points in A is just simply A minus y, giving us our S is equal to A minus y. And lastly, we have to find our S hat vector, which in all cases, if we assume that A is on the positive y-axis, which is what we're focusing on for this problem, then all of the radial position vectors from these wires will be pointing in the positive y hat direction, meaning that our S hat in this expression is just equal to y hat. So now we can plug in all of these infinitesimal electric fields from each of these wires, which we'll call dE, and plug in the rest of our expression. From this, if we wanted to find the electric field for any point A on the positive y-axis, we just integrate both sides. Now, for the bounds of our integral, because we're only dealing in the dy or y with respect to the y-axis, each of these wires will go between a negative L and a positive L on the y-axis. So basically taking all of these wires along this strip of charge. After running the calculations, what we're going to end up doing is getting rid of these y variables through that integration process, and we're going to be left with an A. Now, with that A, we can convert it back into a y variable after our integration expression. And the reason being is because if we basically make this point any y distance from the center of the charge strip, then we are able to say that the electric field at this point y, some distance away from the charge, is the electric field at that point. So we're basically just replacing our variable after the integration expression with y. And after running the calculations, we get a little something like this. I also forgot to mention in my calculations that because we're changing this S hat into Y hat, we have to factor that into our expression for both the integral and the electric field from each of these lines. But at the end of the day, we get this expression for the electric field at any point y along the y-axis.
Alrighty, folks. Now that we've got our lovely electric field equation with respect to y, what we're going to want to go ahead and do is find the voltage potential for any spot on this y-axis from our charge strip. Now, how we're going to go about doing that is by taking the integral of the electric field with respect to some dr vector, a distance away from our charge source. Now, we want to find this voltage potential with respect to y, and we already have our integrand for this integral, which is our lengthy expression for the electric field, which we go ahead and plug into here. Alright, the things now we're going to really want to look for is what that dr vector represents, as well as our initial and final bounds for this integral. So, the way we're going to do that is by considering what this integral is actually doing. Well, the electric field is passing throughout this entire space with respect to y. And what we're going to want to do is find some infinitesimally small section of the y-axis which we'll call a dr, that accumulates the difference in the magnitude of the electric field from this point to this point on this very infinitesimally small section of that electric field. Now, this is represented as a vector, and it is also a representation of accumulation. But we have a leg up in this race. This dr, going from some potential to some other potential, we can just rewrite as dy, because the dr axis that we're interested in, i.e. changing with respect to y, is also just that exact thing, changing with respect to y. So we also want to consider our r vector. In this expression, this r vector, or more specifically the dr vector times r hat, is sum of this accumulation and then multiplied by the r, which is the distance, basically the distance from one point to the other, sort of like a position vector. And again, we have a leg up in this race because we are going from some smaller point on the y-axis to another point further down the y-axis. Well, what does that mean for our r vector? Our r hat vector is just going to be equal to the y hat vector. So our dr vector quite literally just becomes our dy times the y hat vector. This is amazing. So now we are looking for our bounds of integration. This is where things get a little funky. In the setup to our problem, we are defining a distance 2L from the center of the strip of the wire to have a voltage potential of 0. Now, what does that mean? Well, we've basically defined a reference voltage in this entire setup for our problem. And what we want to do is consider what the voltage potential looks past and behind that voltage set point with respect to our charged object creating this electric field. And the way we can do that is by, let's say we have some arbitrary point y on the y-axis. The distance between this point and this point will present some potential voltage difference. And what's really awesome is that the potential difference is just equal to the potential at this point. And the reason being is because the voltage difference is this voltage minus 0, which comes out to just be this voltage. So at the end of the day, what we're really integrating with respect to is from this starting reference voltage to some distance of our accumulating all of these infinitesimal sections of the electric field throughout this space. And what's really awesome about this as well is we can just also invert and collect things that go from the part of the positive strip, so like between L and 2L, as opposed to just doing 2L and beyond. So our integral accounts for everything in between and actually shows up to be the case in our graph. So we now are plugging in our bounds. We're starting at that reference voltage point, 2L, and going to some distance y on the y-axis. Now, it may seem a little weird that I am using a y in our bounds for a dy integral. And what that's in reality going to do is that when we take this integral, all of these y's are going to disappear because we are integrating with respect to some constant bounds. But with one of the bounds being a y variable, it'll eventually create an expression of potential voltage with respect to that y variable, essentially take care of all of our things that we didn't account for. I forgot to plug in our dy with respect to y hat. And now we are prepared to take this rather nasty integral, and I've gone ahead and done that ahead of time, and we get this expression for the potential voltage with respect to y.
At the end of the day, after plugging this lengthy expression into computer analysis, this is the equation we get for the electric potential with respect to a y distance away from the center of the strip of the charge. And with that equation, we'll toss it on to sense making with Ella. Thank you.
Hey y'all, my name's Ella, and today I'm going to be recording the Make Sense of Your Work section. So first, one of the most important / kind of simple ways to check if a equation makes sense is to check for the units. So if you plug in everything into the equation for the voltage, which is a big mess, a lot of it's going to be unitless because of the ln values. So what you end up getting ends up checking out to newtons over coulombs times meters squared. It all ends up canceling, and you end up getting newton meters per coulomb, which does make sense because voltage is joules per coulomb. The equation for the electric field is similar. The unit that you're looking for is newtons per coulomb. And once you plug everything in, also the ln values, everything cancels. You end up getting newtons per coulomb, as you can see in the work here. Now, does our equation make symbolic sense? For this problem, our group's initial prediction was that the charge density would be linear. Starting out at negative, it would hit 0 at the origin and then become positive from that point on. So in other words, from negative L to 0, it's going to be negative, and then from 0 to positive L, it's going to be positive. While it is not uniform, that is something that we had to end up figuring out in our equation section, in our calculations. We ended up finding out that it was a natural log graph, which did match up with what we originally thought it would be. Whatever L value was given, for example, in the graph in the bottom right, whatever L value was given, that's where it started. So in this Desmos graph, the L value given is 2. If you put it at 1, it would be less steep and would just start at 1. The higher you go, the steeper it gets. Yeah, basically, highest amount of voltage is a higher or increasing surface charge. So that's also our electric field up in the top right corner, which we also predicted would be right, that it would be going this way, starting at negative L, positive L, and then in between, there's not going to be, well, it's going to be electric field going that way. So this is our reflection. These are a few problems that we thought were similar to what we ended up doing. So our example 1 is the practice quiz number 3, problem 4b. This problem asked us to find the charge density on an infinitely long strip, which is exactly what this project is asking us to do. So we were able to find the solution as almost like a stepping stone to show us what the right approach was. So for example, we did realize that we would need to divide the strip into infinitesimally small pieces as part of like chop, multiply, add. Additionally, we have a second problem, homework number 3, activity 3, real world context, asking about a straight wire with one end at x equals negative L and the other end at x equals positive L. It has a total charge of whatever value and it's distributed uniformly. And then it's asking us to find the electric field at a point on the axis of a distance from the center of the wire, which is also a large part of how we found our electric field. So we realized that it was imperative that we used integration, especially because it was a non-uniform field, which is again another chop, multiply, add strategy. So both of these problems basically just saying how important it is to use some form of chop, multiply, add to find the answers. Thank you guys for watching. I hope you guys have a great day. Bye bye.